Hey everybody, so I'm just going to try to run through a quick video on conditionals, both regular conditionals and biconditionals. So let's just go ahead and jump right in. So first things first, let's look at this proof with three premises. So the first thing we always do is throw the conclusion at the end of the proof. Now, this conclusion doesn't have any main connective, so there's no introduction rule for us to be thinking about at this point, at least. Instead, let's think about just the elimination rules for the main operators of our premises. Okay, first things first, we have this and. So the easiest thing to do is do an and elimination. So we can do that right away, P and Q. And so we just do an and elimination. So this should be just automatic. If you were watching the first one, or the first video on conjunctions, and elimination, conjunction elimination should just be completely simple and automatic at this point. Okay, now let's take a look at our other premises. The main operator here is a conditional, and here it's also a conditional, right? We can't do an and elimination here because and is not the main operator, right? And we always have to be looking at the main operator. So if we wanted to do a conditional elimination on this conditional, well, let's go ahead and just take a look at what the rule would be asking for. Conditional elimination. Well, it says, if you have some conditional that says P leads to Q, P being true will entail that Q is true. And then you can also point out that P is actually true. Well, then you know Q is true, right? So you can think about this as cause and effect. Now, not every conditional is cause and effect, just to be clear. Like, for instance, being in Texas entails that you're in America. If you're in Texas, then you're in America. But that's not cause and effect. That's just geography. But a lot of conditionals are causal relationships. Like, if you rob a bank, then you go to jail. And so if you rob a bank, then you go to jail. And you really did rob a bank, well, then you know you're going to jail. So if robbing a bank leads to jail and you really did rob a bank, I mean, there's no mystery here. It's just jail, right? So that's all that conditional elimination is saying. So conditional elimination just says each one of these is, you can think about it as a cause and effect relationship. Again, that's not, in real life, not every conditional is a cause and effect. But just to get this rule straight in your mind, you can think about it as P causes R. So the point is, if we know that P happened, then we know that R happened. So at the end of the day, on a conditional elimination, notice what you always get. You're always going to get the consequent, the right-hand side of that conditional. It's always, the conditional is saying, if something happens, then another thing happens. And so anytime you do a conditional elimination, what you get is that effect, is that other thing happening. But the thing you need to feed it is not just the conditional. So we're going to get R out at the end of the day because that's the right-hand side of our conditional. We're just matching what the rule says. But we don't just cite the conditional. This is just saying, if you rob a bank, then you go to jail. But that doesn't mean I go to jail just alone. That doesn't mean I go to jail. I also need to know you actually robbed the bank, right? Robbing the bank and the fact that robbing the bank leads to jail, that's what entails that I'm going to jail, right? Just robbing the bank doesn't mean I'm going to jail. And just robbing the bank entailing going to jail doesn't mean I'm going to jail. I need both of those pieces. I need the fact that robbing the bank will lead to jail time, and I robbed the bank. Now, because of those two facts, I'm going to jail, right? It's the same thing. I don't know why my head is on crime right now, but right. If you committed a crime, then you should pay the penalty. But that doesn't mean you're just going to go pay penalties. You need to also know that you actually did commit the crime. Okay. So, and just to be clear, what about selecting this guy? Why couldn't we do conditional elimination with that? Well, the reason is because this is saying P will lead to R. You need to give it exactly what it wants. It's saying P will lead to R. It's not saying P and Q will lead to R. Sure, you may be clever enough to see, well, if P and Q are true, well, then P is true, and so P is going to lead to R. But that's the sort of process, that's the sort of thinking that you need to make explicit in the proof. That's the point of doing this proof, is you first breaking down, oh, P and Q will give me P. And now I'm going to use this P with this conditional, and that's what gives me R. So a lot of times, so when we just started this problem and all we had were our premises, we couldn't do the conditional elimination. What we had to do first was we had to tear off the P, and then it's ready to be built, or it's ready to go into the conditional elimination. And that's how we get the R. Okay, so down here we have R. We're not going to cite that. We're going to just cite the left-hand side and the conditional, and that's what gives us our right-hand side. Okay, what about our last premise? So this is the only thing we have until, so we've eliminated this main connective, this one, and now this one is the only one left. But to eliminate this conditional, we can go down, we can select conditional elimination. And maybe the first thing to note is, what is the right-hand side of this conditional? Because that's what we're going to get out on this line. It has nothing to do, so whatever the right-hand side of the conditional we're thinking about, this guy, whatever the right-hand side is of that, that's what we're going to get out for conditional elim. Because that's all that conditional elim does. It just gives you the right-hand side of some conditional. So the right-hand side of that conditional is really just S, right? So really, if we could get to S, then we really just got to our conclusion. So we know that that's going to be the last line of our proof. If doing this rule, if doing conditional elim on this premise, if you do conditional elim on this premise somehow, the only way conditional elim ever works, I can only say this so many times, is, well, it's going to give you the right-hand side of some conditional. That's what conditional elim gives you. Always and only gives you the right-hand side of a conditional. And I'm going to say that again, just because I know I'm still going to get questions on it. Conditional elimination only and always gives you the right-hand side of a conditional. It never gives you the left-hand side. You need to come up with the left-hand side on your own. So you know that this will lead to S, but you can't just, but you need to come up with this actually happening. So robbing the bank will lead to jail time, but you can't just, based on robbing the bank leads to jail time, you can't just say, oh, then R and Q based on this guy. That doesn't, again, that doesn't make any sense. You're not thinking about the way these sentences work. You're not thinking about the way these rules work. You need to somehow come up with this left-hand side on your own, ignoring this conditional for the time being. So out of principle, if you're going to do a conditional elim, you're not going to be able to, and you're trying to build the left-hand side of that conditional, you're not going to be able to build it out of that conditional itself. Right, and if you're confused on why, or you want to talk about that, go ahead and email me, but I don't want to waste too much time getting in the weeds on something like that. The point here is, what we're trying to do is we're trying to do a conditional elim on 3. We know if we're doing a conditional elim on 3, well, what we're going to get out at the end of the day has to be the right side. And so that's, so once we get that, then we'll be done. And similarly, because it's a conditional elim, we need another piece. We need somehow to have this left side on its own line. So the idea is we need to build that left side on our own, and then we're able to do conditional elimination. So, well, we already have R, and we already have Q, and we're just trying to build this conditional, or that antecedent, right? We can think about it as, well, if I could just get R and Q, I don't know how yet, but if I could just get those two things, then I could get my conclusion with conditional elimination, right? And all this just comes because I said I want to eliminate this conditional, and then I'm thinking, well, how would that have to look? Well, it would have to give me my conclusion, so I know I would be done, and I would have to first have this left-hand side. So now the real question is just, how do I actually get to that left-hand side? Because once I get there, boom, my conclusion comes for free through conditional elimination. So now I'm just thinking, how do I get to R and Q? Well, look at that. I have R, I have Q. And if you watch the conjunction video, that's more or less, that's the second easiest thing you can do. Just conjunction introduction. Right. So that's really all that conditional elimination is. It's actually fairly straightforward. And I want to go ahead and share screen real quick. It's very straightforward, in fact. So let's say so I want to just show you this again. Let's say we have a proof. And on line 10, you have that you got, I don't know, K from 1 to conditional elim. Okay. Well, again, just like before, just seeing this, think about if you're grading it, or think about how the problem is grading it. If it sees that you're getting K from 1 to conditional elim, then you know, you don't know everything about 1 and 2, but you know a lot, and you know a lot of how it has to look. Well, first of all, one of those lines, you're not sure which, has to have a conditional, of course. Secondly, what else do you know about this off the bat? Well, that conditional, where should K occur, for instance? You know you're going to get K out at the end of the day. So then where did K have to occur up here? There's 3 spots, 1, 2, and 3. Well, conditional elimination only ever gives you the consequence of a conditional. Consequence, you think about those together. All right, so so this is the payoff of the conditional. That's why we get it down here. So again, these are self-checks you can give yourself. After you've done a conditional elim, just go back and say, okay, let me make sure, was that the right-hand side of my conditional up here? Next, you don't know exactly what this could be. This could be J, this could be P, this could be Q. But whatever it is, it just has to be the same as what's right here. Those line 1 and line 2 just have to be exactly the same. So this isn't just any random stuff. This is the same stuff. It has to be some sentence in exactly that same sentence right here. Okay, so again, anytime when you're, or maybe you aren't sure what you're doing wrong, why something's not checking out, think through this process. All right, if I'm doing a conditional elimination on 1 and 2, then either 1 or 2 needs to be a conditional. And secondly, that conditional needs to end with whatever I'm trying to get out at the end of the day. And third, the left-hand side of the conditional better match the entire other line. So this is how conditional eliminate. Again, shouldn't be any mystery here. There's no subproofs. If you're thinking subproofs, you're just not understanding this this rule. So you should go ahead and email me, because all this is, there's nothing hypothetical about it. Stuff will really lead to K, and stuff is actually true. That's what line 2 is saying. So therefore, we actually have K. That's all. There's no subproofs here. If you had a whole bunch of intermediate steps there, then it has no effect on this conditional elimination. There's no point to me skipping steps there. All I'm doing is showing, if at some point you see conditional elimination on some line, you just find those 2 lines and you know a good amount of how their structure should be. Anytime you see conditional elimination, you should be able to come back here and you should be able to find what are those 2 lines, and one of them should look like conditional, and then my new line, and the other one should look like the antecedent of that conditional. Okay. But again, we're not assuming anything here. It's just cause and effect, and then you cause it, and now we get the effect. Okay. Again, I want to stress, though, that these conditionals aren't always, right. In the real world, conditionals aren't always cause and effect. We have geography too. So this is just, but it can be helpful to think about them in these proofs as cause and effect, just to get the idea right. Okay, some logic professors are very emphatic about making sure people don't think about conditionals as cause and effect, because there surely are non-causal conditionals, but that's a bit more philosophical than I think we need to get into at this point. Okay. So now let's go ahead and look at conditional introduction. So conditional introduction is so it is certainly the most straightforward subproof method. Okay. In fact, this is the subproof method that's typically, or is often taught first, because it just fits right in with what's going on with the conditional. So again, we're always going to start our proof with it in the same way. Oops. So, and I already, so the same way, I'm just going to put in my conclusion at the bottom, and immediately I'm just going to think of, okay, what's the introduction rule for my main operator? This negation is only applying to the Q. This arrow is attaching the J to the not Q. So it's the arrow that's my main operator, right? That just comes from truth tables. And now I think that the program is annoying and it pops up the wrong rule. And now I think just what's conditional introduction rule asking for? Well, think about what a conditional is saying. It's saying that P leads to Q, right? If P is true, then Q is true. So this really should be no surprise that the only thing you need if you're trying to show that P leads to Q is a single subproof that shows if you assume P, then you get Q. If you can make that work, well, then you've shown P leads to Q. There's no mystery here. So if you want to show that J leads to not Q, well, we're just going to assume J is true. And then we're going to show that if you assume that, somehow J is, or not Q is going to end up true. Right? That's all that conditional intro is. It is the most straightforward subproof that you can set up. You just take that left-hand side, that's what you assume, and then you put the right-hand side at the bottom. Because if you understand subproofs and you understand conditionals, then you should already, you probably don't need to watch the rest of this this proof. Well, I guess we'll be doing the inside. But in terms of just getting straight on conditionals, there's really nothing else more here. You're just saying, if the left-hand side is true, then the right-hand side is true. So if that's what we're trying to prove that the left side will lead to the right-hand side, well, then all we need to do is just show that assuming the left-hand side leads to the right-hand side. I don't know that J is actually true. I don't know that not Q is actually true, and that's not my goal. My goal is just saying, if J was actually true, if J were true, then I'll be able to walk you down and show you that not Q is also true. And that's exactly what it means to say that J will lead to Q. It's just assuming J will really end up leading to Q, or not Q. Okay, so again, conditional intro is extremely straightforward. All you're doing is just taking that conditional and putting the left side up at the top of a subproof, putting the right side down at the bottom. And now look what we've done. We've made this problem easier. Before, we just had these two premises. And just with the two premises, notice there's nothing you can do. This tilde is just a single tilde on the outside, so we can't do a tilde elimination, right? The only way you can do negation and elimination. The only way you can do a negation elimination is if you have two negations next to each other. So that means it's just impossible to eliminate that negation. So it's not clear what we're going to be able to do at this line right now. We'll talk about this in a second. Here, if we're just looking at the premises, we weren't able to eliminate this this conditional either, because eliminating this conditional would have required that we had the left-hand side. It would have required that we had that spark on its own line somewhere, but we didn't have J on its own line somewhere. But now that we have this subproof, and now that we're just inside the subproof, we're just worrying about how does J lead to not Q. Now we, in effect, have an extra premise. So there's really an assumption, technically. But we're saying, but basically, instead of having a two-premise proof with this really ugly conclusion, now just think about this as a three-premise proof with a much simpler conclusion. So you have more resources to work with and a simpler target to get to. And that's what happens every single time you do a conditional introduction, because you're going to tear this off and it's going to become a new premise, and this is going to become your new conclusion. So again, conditional intro always makes the problem easier. Right. Sometimes you can be really clever and do it without, or doing it in other ways. If you are confident and clever enough to do that, feel free to try, experiment. But otherwise, I always just follow this. Anytime I see a conditional as my conclusion, I just think, oh, cool, this is going to be easy. I'm just going to set up a conditional intro and then do the easier problem. Because now that I have my J, Now I have a perfect match for conditional elimination on 1, right? So if J is true, then this stuff is true. J is actually true. So J leads to that stuff. That means I actually get that stuff, right? That's just simple conditional elimination. Okay. And so then, because I have an and, I can just tear it apart, because I remember that's what I should always do when I see an and. Okay. And now you might hit a wall, because we have, if you just scan through the things, through the lines, we've already eliminated this one. It's impossible to eliminate the main connective here. This one doesn't have one. Already eliminated this one. This one doesn't have one, and this one doesn't have one. So I just went through the list and asked, have I eliminated the main operator of this line? And I either said yes, or it's impossible. It's impossible, yes, it's impossible. So there's nothing here that it's possible to eliminate that I haven't yet eliminated. So in a sense, we kind of run out of steam. We run out of things to do there. But notice your conclusion is a negation. So let's just think, what's the intro rule for negation? And the intro rule for negation just says assume the opposite, get to some contradiction, and then you get not Q. Okay. So I mentioned earlier, it's impossible to do anything with this line as it stands, like in the sense that we can't do an elimination rule on this line. So that should give you, that should be a flag or a hint that really what you're going to need to do is you're either going to need to contradict this line, or it's going to need to be like the antecedent, like the cause to some conditional. If it was the left side to some conditional, you could work with it, to some other conditional. But otherwise, oftentimes, if you just have a tilde on the outside of a lot of junk, then really what you should be thinking about is, how do I build this stuff? Because if I could build this stuff in some subproof, then it would contradict the entire sentence. So again, if you find yourself with a single negated sentence up here as a premise, well, you're not going to be able to eliminate it. So oftentimes, really what you should be thinking about is aiming towards some sort of contradiction with it at the end of the day. Okay. So here, what would contradict with 2? Well, 2 is saying not stuff, so we just need stuff. Stuff is just M and Q right there. Well, look at that. You have Q, you have M, and the second easiest rule is just to put M and Q together with nothing other than conjunction introduction. And then when I do that, now I have a clear contradiction. I have stuff and I have not stuff. And again, if any of this wasn't super clear, like if you'd rather me just go back to the old algorithm, it's the same thing in the sense of you just go back here, see what does contradiction intro need. Oh, it needs P and it needs not P. And then you think, oh, I've got not something here. How do I get P? P would be M and Q. What's the introduction rule for and? And just requires M and. So it's the same thing, but hopefully you're getting a little bit more natural and you can be doing those sorts of steps in your head. Okay, and here I should totally cite what I need to cite. Right, and I should have checked this off if I didn't right away, just to show you that all I need to do in order to get this conditional, if J then not Q, is set up, start with J, end with not Q, and that's going to be happy. Okay. All right, so that's that one. Let me go ahead and do this other one on just conditionals real quick. It might look really nasty, but I just want to prove the point that conditionals are actually really easy, and you should be excited when you see a conditional down there because it's just going to make your proof easy. So I'm just going to copy down my conclusion right here. Okay, and then again, I'm trying to show you this is something that you should all be able to do already even. Just if you're following the algorithm, just first things first, what's my main operator? It's a conditional. Okay, step 2, intro rule for the conditional. What is that? It just says start a subproof. The subproof should, if I'm trying to show that P leads to all this mess of stuff, then I just need to start with P and somehow end with all this mess of stuff. I'm not going to worry about how I'm going to end with all that mess of stuff right now. All I'm going to do is just set up exactly what it tells me to set up. So it says start a subproof with P, end with A and B, entailing C implying P. Right, this is something we should all be able to do as of right now. All that I'm seeing is conditional, cool, I'm splitting it up. No magic, no critical thinking even. Just following exactly what the main operator is telling me to do. Now I'm forgetting about that outside structure and I'm just working with the inside structure. I'm just figuring out how do I use P, or how do I get from P to here? Well, again, this is an iterative process, which means you just keep repeating it. Well, what's the main operator of what you're trying to get to? Oh, cool, it's a conditional. I love those because now I just get to go over conditional intro. I get to see. So that's negation intro is frozen there, don't get confused by it. Conditional intro. Oh, if I want to show that P leads to Q, if I want to show the left side leads to the right side, I'm just going to take whatever my left side is and get it to whatever my right side is, right? It's going to keep getting smaller. A and B, that's my left side. And I need to show that that gets me to C, arrow, P, right? Because that's exactly, so just like this thing just means, so that subproof, assuming P leading to all that junk at the bottom, that's exactly what that last line means. It means if P is true, then all this junk is true. And similarly, what this statement means is if you assume A and then you land at C implies P, then you've shown A and B imply that C implies P. So we're just following the structure. And now again, what's our main operator down here? Okay, it's a conditional. So I'm just going to do conditional introduction again. And it's just going to say, do the same thing. Do a subproof where the left side starts up there, the right side goes down there. That's exactly the form, right? So there should be no mystery in any of this. All that I'm doing when I see that I'm trying to get to a conditional is I'm just tearing the left side off and putting it up top of a new subproof and putting the right side at the bottom of that subproof. That's all that we're doing. And now we just need to figure out how do I get from C. I get to use all of these assumptions just to get to P. So I don't even need to do any and elimination because I know that that doesn't make a difference because I already have P, right? Right, these subproofs, we're just saying we're assuming P. Now, already we didn't stop assuming P. We didn't end that subproof. Now we're on top of that. We're also assuming this. We're also assuming this. I don't really care. All I'm going to do is repeat the fact that we already said P. Now, but the real point of this proof is just to show you when you have just conditionals as your conclusions, you need to be comfortable with this iterative process of, okay, first, set this one up. Now, what's my conclusion here? If it's a conditional, you just set it up again inside it, exactly how the rule asks you to. So again, conditionals are not scary. Okay. Real quick, biconditionals. So biconditionals, the elimination rule works in just the same way as the regular conditional elimination rule, but now you can go both directions. So not only does A cause B, but B will also cause A. Right, so now, so we want to get to not A down here. Now, we can't just do a simple biconditional elimination there because, well, that's not, well, first. Well, so yeah, let me show you. We can't do that because not B is not exactly the right-hand side of this condition or this biconditional, right? Biconditional elimination requires that you have exactly the left or exactly the right-hand side of some biconditional, right? So here we would either need to have exactly A or exactly B if we wanted to do a biconditional elimination. So we're not going to be able to do a biconditional elimination down here. Instead, no, rarely, if ever, start with an elim rule down here anyway, so that should already flag you that that's kind of off. Instead, let's think about the introduction rule for the main operator of the conclusion. The introduction rule is just a tilde, excuse me, negation. A lot of books call it a tilde, by the way. If you're confused, this is why I'm calling it that. So we know how to do that now. We've done that a lot. Every time I need to do a negation introduction, I just assume the opposite of what I'm trying to prove. I get it to some sort of contradiction. And now, because I am good and responsible, I am going to make sure this checks off before I even proceed, just to make sure that I trust myself about where I am and that I don't go back on it later, because that happens all too often. Now recognize what you have. Now you actually have exactly one of the sides of that biconditional. And so that's going to give you exactly the other side of that biconditional. That's what biconditionals do. They say, if A is true, B is true. If B is true, A is true. If you can show me one, I'll show you the other. And so all you need to do is show one. We just needed to have A already, and then we can do biconditional elimination. Why do you know that B is true? Well, because I know A is true, and A always comes with B. Right? Just think about each one of these steps. You should be able to just intuitively think about the logic of, okay, why does this one thing come from the other two things, ignoring everything else in the problem? Well, A is true, A leads to B, so B is true. Boom, done. All right, now I have B. Remember, I'm trying to get to a contradiction. Well, good thing I have B and not B right there. Contradiction, introduction. Okay. Right, and because I set it up right in the first place, because I already checked this off, I know I'm done, right? I know as soon as I got that, I don't have to think, oh, do I need any set? Do I need a contradiction elimination or anything like that? Do I need any other subproofs? This is, if you're doing this in the right steps that I'm showing you, then there's no second guessing to go back on and wonder, do I need more subproofs or do I need something else? After we checked off that this negation intro works, you know that this has to be the last line of your proof. That's why negation intro is happy. So trust yourself as you're going through these things. Finally, let's just look at a biconditional introduction. So biconditional introduction is really just as easy, maybe a tiny bit. It's just more things to do, but it's just the same as a conditional introduction, right? If all this is saying is two things, it's saying P arrow R, and then it's saying R arrow P, right? That's all that a biconditional is saying. It's saying P will give you R and R will give you P. So it should be no surprise that when you're doing a biconditional intro, of course, that when you're doing a biconditional intro, you're just doing two conditional proofs. You're just showing that P will lead to Q and Q will lead to P, and that's exactly what it means to show that P and Q will lead to each other. They always come together. P if and only if Q. Okay, so that's all we need to do. We just need to set up, excuse me, one subproof that shows that P will lead to R, and then another subproof that shows that R will lead to P. Right? That's exactly what the rule is asking for. If you want that biconditional, all you need to do is have two subproofs. One subproof starts with the left, ends with the right. The other one starts with the right, ends with the left. And now as soon as I have that, I'm going to check it off. And now I know, okay, I'm good on those. I'm never going to change how these start. I'm not going to change how these end. This is how the proof is going to work. All right. So now that I have, now the task is just working inside. So how do I get from P to R? Well, you should first notice we haven't talked about eliminating any of the operators up here. And because we don't have any main operators on our conclusion, on our new mini conclusions or sub-conclusions, there's nothing to think about introducing. So instead we can think about eliminating up here. To eliminate this conditional right here, well, what would we get out of it first if we did a conditional elim on one? Well, you should already know you always and only ever get out the right side. Doing conditional on one or conditional elim on one can only have one result, and that's just Q. Okay. Now, So that's what we would get out of it if we were able to do it. But we don't know if we're able to do it, or in order to make sure we're able to do it, we also need to make sure what? That we also have the left side already. So the thing we get out of it is Q, but we need to make sure that we already have the P. So the thing you get out of it is jail time, but first we need to make sure that you actually robbed the bank. So this says robbing the bank leads to jail time. Here, you actually robbed the bank, and that's why we're able to conclude that you're going to jail. This is just conditional elimination. We're just saying P really leads to Q, and P is actually true. Therefore, I have Q. So right, a conditional elim is always going to take those two pieces there. Before we assumed P, we weren't able to do a conditional elimination because all we had was the conditional. You always need to already have some P floating there, whether an assumption, whether it's a premise, whether it's something you get from a premise. The point is you need to already have that, or you need to be able to build it first, and then you can do the conditional elimination. All right. Now that you have Q, you can do a conditional elimination on 2. Now that you know Q is true, well, Q is just going to lead to R. So now we get R, and R is just going to come from conditional elimination. Because Q leads to R, and Q is true, we know that we have R. And lo and behold, that's exactly where we were looking to get to. So now we're done with that subproof. Okay, now forget about this subproof. Now we're just working on this one. So we can think, how do we get from R to P? So we can go ahead and just skim through our premises just one more time. And so first off, can we eliminate the conditional up here? We're able to do it in this subproof, but can we do conditional elim on 1 now? Well, first, what would it give us? It would give us Q if we were able to do it, because it always gives us the right-hand side of the conditional we're talking about. But what would we need to have already? We would need to have P. So we know P leads to Q, but we can't conclude that P is true until we already know that P is true. And in this subproof, we don't have P, and we don't have P in any premise. The only reason we had P up here was because it was the assumption of this subproof. But here we're in a different subproof, and we don't have P at all. So we cannot do conditional elim to 1 in this subproof. Can we do it to 2? Well, so doing it to 2 would give you R, which, by the way, is useless. So that should give you a hint that there's no reason to do this anyway. And secondly, we're not even allowed to do it because we don't have Q. Sure, Q would lead to R, but we don't have Q in the subproof or in any premise. Again, we need to ignore the other subproof that we have. So there's no way to eliminate either of those. The third premise is another one of those negated sentences, but it's just a single negation, so we can't do negation elimination there. So that should tip you off into how to use that sentence once again. So instead, we will do what you do when you hit a wall. If the last resort is proof by contradiction, which is especially helpful when you have an atomic sentence down here. So if you want to prove that P is true, we're just going to assume that it's not true, show that that leads to a contradiction, and that's how we know that P is true, right? So this is just the other version of negation intro. So you could, if you're not comfortable with this, you could be thinking about it as that, and then you just do a double negative or a negational in there. But for whatever reason, the program is lax enough, or there's reasons for it. And I would rather keep it super disciplined but I mean, it's fine. As long as we all understand why this works, that's what's important. And the point is, it's the same logic as regular negation intro. We're just saying, if you want to show that P is true, suppose that it's false, lead to a contradiction, and that's exactly what shows, right, that P is actually true. Okay, so now the question is, how do we get to a contradiction? So if you've forgotten, you just do contradiction intro. Oh, what's that? It just needs something and not something. Well, again, we have this line up here that we're not able to use because it has just a single negation. So a good hint is this will probably be my not something. So now it's just, how do I build my something? Well, something is just, so the question is, how would I get R and not P, because if I could get that, well, that guy is going to contradict with that guy, and then I would be happy. And so how do I get R and not P? Well, this is just a conjunction, which just means I need to find R and I need to find not P. So I found not P and I found R, and I just stuck them together with conjunction. Okay, so that's all that one is too. Right, so again, biconditional introduction is, if you understand conditional introduction, there really shouldn't be any confusion on biconditional introduction. You're just doing it like you would a regular conditional, and then you're just doing it again, but the other way. And so again, you should be happy. I mean, other than the fact that you're going to have to do basically 2 subproofs here, 2 proofs, like this will make your problem easier when you set it up as a biconditional. I also want to just throw, all that I do when I'm setting up these problems is I just throw a valid argument up there. I come up with it on the spot right before these videos. And then one that I know will at least need to use the rules that I'm talking about. But like, I don't have any specific proof strategy or like any strategy in mind when I'm setting up the problems per se. So I just want to make sure you're all aware that none of these are carefully constructed for any particular purpose other than the fact that I know I'm going to use the rules I want at least once. So it's not that I'm thinking, oh, I want to show you when you have a negated sentence like this, here's a good hint. So these are just helpful things to pick up along the way. But the most important thing to be gaining from this video particularly is just the elimination rules, that they always have to cite 2 lines, some conditional line, and then the spark for that conditional. And then the introduction rules are really straightforward too. Just you need, for regular conditional, you just put the left side on top and the right side on bottom. And for the biconditional, you just do that, and then you just do it again, but the reverse. Right. So there's nothing special about these problems. All that I'm doing is just following this algorithm of just starting at the bottom, thinking about the main operator and thinking about how to introduce it. And then just once you have that set up, do it again. Think about where am I trying to get to now and how do I introduce that? Okay, go ahead and email me if and when you have questions.